You're watching a Channel 98 NBISD TV production.
Hello out there in TV land. Welcome to another mathematically invigorating episode of That Geometry Show. As always, I'm your groovy host, Kevin Corpy, and today's episode is a dandy. We're going to be talking about basic logic, if-then statements, and deductive reasoning, so you're not going to want to miss a bit. Now remember that every little document you see me working on today's show is available for you to download at home, full-size version, for the cost of $0. It's free. Just go to the website, www.newbraunfels.txed.net. All right, enough of me rambling on about this. Let's get on to the show with me rambling on about the lesson. Yeah, let's do it. All right, lesson 4 is going to correspond with your Glencoe Geometry textbook, chapter 2.2 and 2.3. Again, we're talking about if-then statements and deductive reasoning. So by the end of the lesson, you should be able to write a statement in the if-then format. You should be able to write the converse, the inverse, and the contrapositive of an if-then statement. You should be able to understand the laws of detachment and syllogism, 2 laws there, and you should be able to appreciate a simple ham sandwich. More on that later. All right, if-then statements. An if-then statement is a form of deductive reasoning. That is just what the name says. We assume that if the if part is true, then by what we call the law of detachment, it automatically follows that the then part is always true. The previous statement that I just read is one such statement. Here's another one. For example, if you are watching this show, then you will learn something about geometry. The law of detachment basically says that if this is a true statement, and if we are in fact watching the show, then you will learn something about geometry. It's a conclusion that we can make. It's called deductive reasoning, and it's basically going from the general to the very specific. Now, in terms of geometry, we can look at this example. If point D is between point C and point E, then we know the measure of segment CD plus the measure of segment DE has to equal the measure of segment CE. That was from a previous show. That was the segment addition postulate. Okay, now these types of statements are called, we can have another name for them, they're called conditional statements, or we just abbreviate them as conditionals. Now, an if-then statement contains 2 parts. The first part is the if part, and it's called the hypothesis. The second part is the then part, and it's called the conclusion. So the reason these are conditional statements is because if the hypothesis is true under those conditions, then we can assume that the conclusion is true. Okay? Now, we can also shorthand these if-then statements. So to symbolize an if-then statement, we can let the letter P represent the hypothesis, the if part, and we can let the letter Q represent the conclusion, the then part. So here's some other ways that we can shorthand write the if-then statement. We can now say if P, then Q. We can also say that P implies Q. We can say the same sentence just with symbols by using this single directional arrow, and we read that also as P implies Q. And those are pretty common. You'll see those in your geometry class. There's also some more sophisticated ways to say it. We can also say P only if Q. We can say Q if P. We can then say Q is necessary for P, and we can also say that P is sufficient for Q to happen. All of these are equivalent statements. They all mean the same thing. Again, the ones you're probably going to be coming in encounter with most often are these first 3. Now, deductive reasoning, unlike inductive reasoning. Inductive reasoning is the opposite. It's going from a very specific to a very general. This is kind of drawing a conclusion from something. Deductive reasoning is general to specific. Deductive reasoning is a valid form of proof, whereas inductive reasoning is not. And it is, in fact, the way in which your geometric proofs are going to be written. It's the idea of stringing together logically equivalent statements to go from what you're given to what you would like to prove. by using a series of if-then statements. Now here's an example. A person knows that all men in a certain room are bakers, and we know that all bakers get up early to bake bread in the morning. We also know then that Jim is in that specific room. Now that statement is not written in if-then form, so sometimes just rewriting the statement in that fashion can help clarify. Here we go. We can say if a person is in a certain room, then that person is a baker. Then we can say if that person is a baker, then he gets up early and bakes that delicious bread. Okay? So given those two if-then statements, what can we now say about Jim if Jim happens to be in that specific room? Well, this is where the idea of deductive reasoning comes in. Knowing these statements to be true, a person could deductively reason that Jim, in fact, gets up early in the morning and he has a recipe for that delicious bread, that he actually bakes the bread. That is due to what we call the law of syllogism. It's basically the transitive property for logical statements. So here's how we can write it with mathematical syntax. We could say if P implies Q, and we also know that Q implies R, then we can assume that P, the original statement, ends up implying R. So this is stringing together two logical if-then statements to go from P to R by way of Q. When you do proofs later on, you'll have several of these in a row. All right, now deductive reasoning in geometry is much like the situation described above, except it does relate to geometric terms. For example, a statement could be adjacent angles have a common side. We can rewrite that in if-then format saying if two angles are adjacent, then they have a common side. Okay, so just rewriting it in if-then form. Now, we talked about the statement. It's time to talk about some relatives of the statement. Every statement does have some relatives. The first one we're going to talk about is the converse. And the converse of a statement is formed when the hypothesis, the if part, and the conclusion, the then part, are switched. They're interchanged. So we could write that as, instead of P implies Q, we could say Q implies P. Now the converse in general says something very different than the actual statement. If we look at the statement above, if two angles are adjacent, then they have a common side, we can flip the if and then to get if two angles have a common side, then they are adjacent. What we want to know is that a true statement? Okay? Well, if we can find two angles that disprove that statement, then we say that we have found a counter example. A counter example disproves a statement. And then, if we find one such example, we say that the statement is false mathematically. It's not true, even though it might be true sometimes. In mathematics, if it's not true all the time, we say in general that it's false. Okay? Now, what would finding a counterexample involve in this case? Well, we were saying if two angles have a common side, then they have to be adjacent. So we have to find something that satisfies the hypothesis, namely two angles have a common side, but it doesn't satisfy the conclusion. So let's look at the diagram here at the right. Angle POM, this one here, and angle PON, this one here. They do have a common side. What is their common side? Side PO. But they are not adjacent. Now, why are they not adjacent? If you remember, they have points that are common on their interior. Namely, all these points right here inside angle POM are in common with angle POM and PON. So the side that they're sharing is not the one that's in between them. Okay, so they do share a side, but they're not adjacent. So we just found a counterexample. So in general, the converse of a true statement is not true. Again, even though it might be true sometimes. Let's look at the next statement here. It's going to be what we call the inverse. Okay, now the inverse of a statement is formed by negating both the hypothesis and the conclusion by adding the word not in front of them. Mathematically, you can write that with a little tilde. Not P implies not Q. Or we can use this symbol here, which is like a sideways bracket. Not P implies not Q. So we don't switch the order, we just negate it. So here's a different statement. Vertical angles are congruent. Well, that's nice. Let's write it in if-then form. If two angles are vertical, then they are congruent. By the law of detachment, we know that's true. So if we happen to have two angles that are vertical, if that condition is met, then we know that they'll have to be congruent. That's the definition from last time. The converse would say, if two angles are congruent, then they're vertical. So disproving the converse would require us to find two angles that have the same measure but are not vertical. Well, we can look at this diagram down here and we can find two such angles. Angles PON right here form 90 degrees. And angles QOP also form 90 degrees. They form a linear pair. And they're both at right angles. So these two angles are congruent, but they're not vertical. Because remember, vertical angles are formed by intersecting lines. They're opposite each other. These two angles here would be vertical, and these are not. Okay, so we've disproven the converse. Well, now let's look at the inverse. The inverse, again, is by negating the hypothesis and the conclusion, but not switching the order. So if two angles are not vertical, then they are not congruent. So is the inverse true in general? Well, again, to disprove this, we're going to have to find two angles that are not vertical, but then we're going to have to show that they are congruent. Now, if you notice, the same counterexample that we used to disprove the converse works here as well. Here's two angles, QOP and NOP, that are not vertical, and we already said that they were congruent. All right, so what can we say about the inverse? In general, the inverse then would be not true. There are many other examples where we can find two angles that are congruent and not vertical. I can give you a real quick example right here. Here's an angle that's 30 degrees. Here's another angle that's 30 degrees. Okay? I drew two separate angles. They're not vertical. They're not even basically on the same diagram, yet they have the same measure. So in general, again, the inverse statement is not true, even though sometimes it might be. All right, now it's time to watch some very valuable public service announcements. But if you don't go anywhere, then we will be right back.
There comes a point in your life when you realize you're not a kid anymore. Suddenly, you have to make decisions. You have to make choices every day. This is the time when you define yourself, or you let others define you. You quickly learn that there are two ways to go: under the influence or above the influence. I am above the influence.
We need a leader who's determined, dependable, and completely housebroken. We need Spoiled Yappy Dog. This message paid for by Citizens for Yappy Dog.
If you're not voting, then who are you electing?
Hey, welcome back. Short time no see. If you're still watching, then you're still learning. Let's get right back to it. The next relative of the original statement we're going to talk about is something called the contrapositive. One word, the contrapositive. Okay, now the contrapositive of the statement is basically the combination of the two previous ones, the converse and the inverse. What it does is it negates the switching of the hypothesis and the conclusion. So it's basically the negation of the converse. So instead of saying P implies Q, we'll say not Q implies not P. Or again, using the bracket notation, not Q implies not P. Let's look at that with another example here. Actually, the same one as before. Looking at the same statement, vertical angles are congruent. And again, rewriting it, if two angles are vertical, then they are congruent. The contrapositive would say if two angles are not congruent, then they are not vertical. Now, we've already shown that the converse and the inverse of this statement is not necessarily true, and therefore it's false. But what about the contrapositive? Well, let's see. If we're going to try and find a counterexample to disprove the contrapositive, we're going to have to find two angles that are not congruent and then show that they are vertical. Okay, so let's see. We have to find two vertical angles that are not congruent. To disprove the contrapositive, we're going to find two vertical angles that are not congruent. I'm thinking in my head. Are you thinking at home? Vertical angles. Remember, vertical angles are formed by two intersecting lines, and they're across from each other. Have you found them yet? Dot, 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 simulated? Well, yeah, I haven't either. And there's a good reason for that. We know that all vertical angles are congruent. So you're never going to find two that are not. Go back up to the statement. If we assume that the statement's true, what does our statement say? It says vertical angles are congruent. So the contrapositive To disprove it, we're going to have to find two vertical angles that are not congruent, and that's not going to happen because the statement is true. So we can't disprove the contrapositive. Therefore, dun dun dun, the contrapositive of a statement that is true is when? Always true. But again, the original statement by the law of detachment has to also be true. So here we go. To summarize the contrapositive, if the original statement is true, then the contrapositive is also true every single time. If the original statement is false, then the contrapositive is also false. We say that the two are logically equivalent. They're really saying the exact same thing, whereas the converse and the inverse, we're saying something entirely different. Now, the contrapositive, knowing that it's equivalent, can actually be more useful sometimes than the actual statement when we're testing conditional statements. Here's an example. A statement might be, if some number n happens to be an even number, then it's divisible by 2. Well, stating the contrapositive, we could say, if n is not divisible by 2, then it can't be an even number. Now, why is that more useful? Well, we've just established kind of a criteria by which all even numbers have to pass in order to be entered into the even number club, to be bestowed the glorious title of an even number. Okay? So it's kind of like a checklist that we can use. So let's try it out. Is the number 17 an even number? Well, is it divisible by 2? That's what the question comes down to. If we take 17 and we divide it by 2, do we get a remainder or not? Well, we get 8, and then we unfortunately get a remainder of 1. So 17 is not an even number. Ooh, but what about the number 18? If we divide 18 by 2, we get 9 with the remainder of 0. So this is a pretty easy example. 18 is even, 17 is not. Contrapositive gives us something we can check off. Okay, now, you might have seen this in books or somewhere other than books, like maybe TV or other reading material or non-reading material. But somewhere maybe it's come up that you've seen these if and only if statements, okay? If and only if. Sometimes they're abbreviated IFF or pronounced if. Now these include your postulates that you learn in class and your definitions. So what's with the if and only if? Is it stated like this merely for some type of dramatic effect? Are we math teachers just trying to be adamantly emphatic? Well, the answer is yes and no. Okay? We are trying to draw attention to the fact that if and only if is different from an if-then statement. But no in the sense that it does have mathematical meaning aside from just trying to be emphatic. Here's an example. Two angles are complementary if and only if their degree measures add up to 90 degrees. Okay? Well, that's written as the way it is a postulate. Okay? If you were to write that in definition form, you would just say complementary angles have angle measures that add up to 90. So that's a postulate or a definition. It tells us what complementary angles are. Now, if and only if statements are sometimes denoted by a bidirectional arrow instead of a single arrow, one that goes both ways. Now that has meaning because that means that each side of the argument implies the other. In other words, the hypothesis and the conclusion are interchangeable. The hypothesis is both necessary, we say, and sufficient for the conclusion. And because they're interchangeable, we can write the previous statement, if and only if, two different ways. We can start with one side and have it implying the other. So we could say if two angles are complementary, then their measures add up to 90 degrees. But because it's if and only if, we can actually start with the conclusion. If two angles measures add up to 90 degrees, then they are complementary. And for an if and only if statement, if it's a true if and only if statement, then both of these are going to be true. Doesn't matter which side we start with. Well, that automatically means that the converse of either statement is true. Because that's basically what we did up here. We started with the statement, and we flipped the order to get the converse. So in an if and only if statement, the converse is true. Now watch the logic here. We already know that a true statement has a contrapositive that is also true. So the contrapositive of both of these statements is true, which will imply that the inverse is also true. Wow, isn't logic fun? Okay, so to summarize, an if and only if statement, or an if statement, basically is the only type of statement where all four statements are true. That's, again, under the law of detachment, assuming that the original statement is true. So the inverse is true, the converse is true, the contrapositive is true if the statement is true. But remember, in general, the converse and the inverse are not true. Only in an if and only if statement. All right, now it's time for the segment we call the Say What segment. And today, we're going to obey the laws. So let's obey the laws, please. Let's all just get along here. We're going to go over the laws of detachment and the laws of syllogism again. So let's just jump right in here. The example, the first one I'm looking at is the law of detachment and other laws of logic can be used to provide a system for reaching logical conclusions called, we've got inductive reasoning. No, that's kind of like a doctor diagnosing an ailment based upon your symptoms. He's kind of troubleshooting. His diagnosis could be wrong, okay? That's not a form of proof. That's going from specific to general. Detachment, no, that's part of the reasoning. That says that if an if-then statement is true, and we do have the if part, then we can assume the conclusion's true. Reasonable doubt, well, we're not in a courtroom, okay? So deductive reasoning, that's the answer. The answer is D. D for deductive reasoning, and for D, right answer. All right, the next example. If two numbers are even, there's the if, then their sum is even. If it's a true conditional statement and 8 and 24 are even numbers, then the law of detachment will allow us to reach a logical conclusion. Which one is it? So again, the law of detachment says, assuming that the statement is true and assuming that we do have two even numbers, and we do, 8 and 24. What can we assume using the law of detachment? Well, the law of detachment would say that the sum of those two even numbers, 8 and 24, has to be itself even. That's what the statement says right there. So which one is that? Choice A, the sum of 8 and 24 must be even. Well, by golly, that's nice when it's the first choice. Let's quickly look at the others. If the numbers 8 and 24 are odd, their sum is 32. Well, the theorem or the if-then statement didn't say anything about odd or the number 32, so nope. The sum of 8 and 24 must be odd? Says who? Not the if-then statement. How about this one? If the numbers 8 and 24 are even, then their sum is 32? Well, that just happens to be true in this case. But what if I had two other even numbers? Their sum wouldn't be 32. So it's always nice to look at all the other answer choices to make sure you have the right one. Our statement just makes a conclusion that the sum has to be even. Okay? Next example. If two angles are vertical, then they are congruent. If that's a true conditional, and we do have two vertical angles, say angle 1 and angle 2, so by the law of detachment, which one is not true? We're trying to find the false one. Let's go through all these and just see if they're true or false. Number 1, or letter A. Angle 1 and angle 2 both have a measure of 45. Well, our conclusion says that they're going to be congruent. Well, if they're both equal to 45, they have the same measure, so yeah, they would be congruent if they both measured 45. Part B, angle 1 and angle 2 are both obtuse. Well, it comes down to, can we have two obtuse angles that are the same measure? And absolutely. If they're both 120, they're equal. So they can be both obtuse. Choice C, angle 1 and angle 2 are not congruent. Uh-oh. What did we make a conclusion about up here? It said if they're vertical, then they are congruent. So saying that they're not congruent, well, that's just silly, right? So that one appears to be not true. Let's look at the last one. Angles 1 and angles 2 are congruent. Yeah, well, that's exactly stating what the conclusion is. So choice C is the one that is not true. Almost done. Example again. Which statement follows from statements 1 and 2 by the law of syllogism? Now remember, the law of syllogism is kind of like the transitive property. We're stringing together two or more if-then statements to come to a conclusion. So statement 1, if an object is a square, then it's a rhombus. You'll learn about that later in the year. If an object is a rhombus, then it's an equilateral. All the sides are equal. Well, let's see. The middleman appeared to be rhombus. Square implies rhombus. Rhombus implies equilateral. So by the law of syllogism, we can cut out the middleman. Okay? The square would imply equilateral. So that's the choice I'm looking for. Let's look at the choices. An object is a rhombus. Well, that would be true, but not specifically by our law of syllogism. If an object is a square, then it is an equilateral. Square implies equilateral. That's looking real good. I'm going to circle it, but I'm going to keep looking here. An object is a square. Well, yeah, that's going to be true also, but not specifically what we're looking for. If an object is equilateral, then it's a square. Okay, that's not always necessarily true. Okay, so some of these might be true, but basically by what we're looking for, square implies equilateral by way of rhombus. Okay, so there were some good answer choices in there, but again, only one of them was correct. All right, one last example with the law of syllogism. Which statement again follows from 1 and 2 by the law of syllogism? If two angles form a linear pair, then they are symmetric. Or, I'm sorry, supplementary. Supplementary. S-U-P-P-L. Got it. If two angles are supplementary, then their sums add up to 180. So again, supplementary is linking what we started with, a linear pair, to the measures adding up to 180. So cut out the middleman. Linear pair is going to imply measures adding up to 180. That's what we're looking for. Linear pair implies measures 180. All right, choice A. The measures of supplementary angles add up to 180. Okay, that's true, but not linear pair 180. The sum of the measure of the angles in a linear pair is 180. Hey, I'm liking that one. I'm going to keep going, though, to see if there's a better choice out there. Supplementary angles form a linear pair. Trueness, but not what we're looking for here. Linear pair implies measure 180. Choice D. A linear pair is formed by supplementary angles. Again, nicely stated, but not specifically by our law of syllogism. Now, it's important as you're going to do these proofs in class that you string them together in the right sequence. If they're not in the right sequence, then somebody who's looking at your work is not going to be navigated from start to finish seamlessly through your transitive property, or basically the law of syllogism. So very, very important property. All right. Now, the final example is some fun you can have with the law of detachment and the law of syllogism. All right. So here's one more use, or shall I say misuse, of the law of detachment and syllogism. Can you find the error? Is there an error? Here we go. Here's the statement. Nothing is better than eternal bliss. I don't think anyone out there is going to disagree with that. Nothing is better than eternal bliss. So that would be statement A. Statement B. A ham sandwich is better than nothing, right? I mean, who's going to argue with that? What would you rather have, nothing or a ham sandwich? Ham sandwich sounds pretty good. Now, by the law of syllogism, it follows that a ham sandwich, then, is better than eternal bliss. Wow, you heard it here first. Ham sandwich, better than eternal bliss. That is one tasty ham sandwich. Much better than eternal bliss. But I digest. Anyway, thanks for joining me on today's show. Until next time, I'm Kevin Corpy, and I'll catch you on the flip side.
You're watching a Channel 98 NBISD TV production.